we thought it would be a good idea to start off our video by going over the main components of honey. Honey essentially is concentrated nectar. Worker bees gather nectar and keep it in their honey stomach, transporting it back to the hive where water is evaporated from the nectar and the concentrated nectar is stored in the hive as honey. After being concentrated, honey consists of mainly 17% water, 2 monosaccharides, about 39% fructose and 31% glucose, and the rest disaccharides or complex sugars.
Okay, so in this segment of the video, I just wanted to talk a little bit about the different forms that glucose can be found in. To recap, glucose is the simplest carbohydrate or sugar found in honey and can be readily used to make ATP as energy in the body. The most common form of glucose you're probably used to seeing is the cyclic structure I have here on the right. However, glucose is also present in its chain-like form, which is the form that is most reactive due to the carbonyl present. So the reaction you see here taking place is either acid or base catalyzed, and for example, if it were base catalyzed, you would have deprotonation of the alcohol here in pink from the base, creating a nucleophilic site within the glucose molecule. Up at the carbonyl, you have by default an electrophilic site caused by the polarization of the double bond, resulting in partial positive and partial negative charges. And as they say, opposites attract, and the nucleophile attacks the electrophilic carbon of the carbonyl and forms a cyclic structure shown here to the right. You may wonder why the OH here in pink is the one that takes part in the reaction, and that's basically because of product stability. So the formation of a 6-membered ring that can take on a chair conformation is much more favorable than a formation of a 5, 4, 3-membered ring. So you have the farthest hydroxy group away from the attacking carbon. In organic chemistry, we're not really used to seeing 6-membered rings exhibited using this diagram, and as I mentioned before, you can also draw it in the chair conformation, which I have right here. The final piece of information I have about the forms of glucose is the difference between its alpha and beta forms. You've probably heard of beta glucose before, and that's because it's the most common form of cyclic glucose. And I'll draw that molecule here now for you. And the only difference between beta and alpha glucose is the position of the OH substituent on the carbon here. It has been in red, but at this time I drew it differently. So because the carbon in red here is sp2 hybridized in the chain structure, you can see back here, we actually have possible bond rotation between these two carbons. And so since this reaction is an equilibrium process and both chain and cyclic structures of glucose exist, we have constant spontaneous opening and closing of the ring structures with possible rotation between this bond in between. So that creates both isomers, alpha and beta. And beta is the most common, again because of steric hindrance. The OH is most comfortable being in the equatorial position away from the ring structure, so you're going to get mostly beta conformations instead of the alpha conformation.
As just discussed in the previous slide, glucose has 3 common isomers, 2 in a ring, alpha and beta, and 1 in a chain. One way that organic chemists have been able to determine the favorable conformation is to use NMR, both proton and carbon-13. Shown here are the proton and carbon-13 NMR spectra of glucose, and shown here also are the spectra corresponding to the structures after 24 hours in a D2O solution. The purpose of the D2O was to slow the process of the changing conformations between alpha and beta glucose. The structure of the glucose conformation after 24 hours would correspond to that of a mixture between alpha and beta glucose. The easiest way to determine that this is a mixture of both alpha and beta glucose, is to look at the carbon-13 NMR initially and compare it to the final spectrum. There are initially 6 unique carbons, which is consistent with just having pure alpha glucose. However, the spectra after 24 hours in D2O shows 6 more unique carbons, which must indicate a mixture of both alpha and beta glucose. These NMR spectra clarify that the cyclic conformations of glucose are the most stable, and that the chain is an unstable intermediate between the 2 cyclic conformations.
There are many organic acids found in honey that lend themselves to its acidic nature. Organic acids make up 0.57% of the composition of honey. Some organic acids found in honey include acetic acid, butanoic acid, lactic acid, and citric acid. Honey also contains many aliphatic and aromatic acids, which are important contributions to its sweet flavor. The average pH of honey is 3.9. The heating of honey causes many chemical reactions. Since honey is acidic, this causes natural browning over time. There are two processes that honey goes through. The first is the Maillard reaction. Aside from organic acids, honey also contains amino acids. In the Maillard reaction, these amino acids react with sugars found in honey to cause non-enzymatic browning to occur. At high enough temperatures, a second browning process occurs called caramelization. When heating begins, molecular bonds in honey are broken and the sugar molecules give a brown tint to the substance. One interesting fact about the heating of honey is that when fructose is heated, hydroxymethylfurfuryl, or HMF, can form. HMF is very deadly to bees.
One of the fun things about honey is that it never spoils. This is due to two main factors. The first is the fact that honey is only 17% water. Bacteria has a higher concentration of water than honey, so when it comes in contact with honey, it is dehydrated by it. Also, there are two parts of honey that result from one of its enzymes. One is gluconic acid, and the other is hydrogen peroxide. Gluconic acid is a carboxylic acid that keeps the pH of honey between 3 and 4. In addition to the hydrogen peroxide, it is a very hostile environment for bacteria to grow in. Another fun fact about honey is that it was found in the pyramids of Egypt and was still unspoiled to this day. Okay, so one of the enzymes that bees have is invertase. And invertase comes from the bee's salivary glands. And it catalyzes the hydrolysis of sucrose into two smaller sugars, glucose and fructose, which are found in very large quantities in honey. So what happens is a water molecule, the bond from this its electrons go to this oxygen molecule. This oxygen molecule then has excess electrons to attack the hydrogen of the water molecule. Then this oxygen's electrons attack this carbon's positive charge, so that it forms an OH component. Therefore, the water's OH goes to the glucose molecule, and this oxygen from the sucrose molecule that combines the glucose and fructose parts ends up in the fructose molecule, which can be seen from the different colored O's. So you may be wondering how the invertase from the bee's salivary glands are able to access the nectar. Well, the answer is regurgitation. When the bee comes back to the hive with a bunch of nectar in its stomach, it will spit out the nectar into another bee's mouth, and they will pass back and forth this regurgitated nectar until the invertase has broken down enough of the sucrose molecules into glucose and fructose that they can finally put it into the honeycomb. Okay, there are many other enzymes in honey. Notice that all these enzymes end with the three letters ACE. ACE is at the end of a word symbolizes that it is a catalyst or enzyme. One of these catalysts is diastase, also known as amylase, which breaks down starch into simpler carbohydrates. Scientists are currently unclear on why bees add amylase to honey because there is no starch present in nectar. Another enzyme is esterase, which breaks down ester bonds, and catalase, which converts peroxide into water and oxygen via this reaction. Catalase also reduces the antibacterial effects of honey because it is breaking down the peroxide. Another important catalyst in honey is glucose oxidase. This converts glucose to gluconolactone, which later becomes gluconic acid and hydrogen peroxide. Gluconic acid is the main acid found in honey, and that and hydrogen peroxide both contribute to the antibacterial properties of honey.
Another really interesting discussion about the organic chemistry of honey is the difference between the sugar that makes up honey and table sugar with respect to the effect that each has on the body. Table sugar is a disaccharide, sucrose, that contains fructose and glucose connected together. This in itself is not digested very easily by the stomach. Honey however, is handled differently. As discussed earlier about the reaction between sucrose and the enzyme invertase, the enzymes added to the nectar by bees can break down the sugar into two separate monosaccharides of fructose and glucose. These, on the other hand, are readily available for digestion, whereas table sugars cannot be broken down into glucose until they reach the small intestine. Obviously, this means that honey has some health benefits in terms of digestion.
Did you know if bees were paid minimum wage for their labor, a jar of honey would cost $182,000? This is based on the fact that honeybees produce about 1/12 of a teaspoon of honey in its lifetime, which is between 120 and 150 days.